So today I'll be going over force vectors. Now, before we get into vectors, we need to go on to the definition of what scalar and a vector are. So let's go ahead and do that. So a scalar is nothing more than a quantity that can be completely specified by just its magnitude. In other words, just by a number. So some examples here include length. So length could be completely specified just by a number, let's say 1 feet, 1 meter, etc., so on and so forth. They could be just completely described by just that one number. Another example would be mass, such as 5 kilograms, 25 kilograms. It's completely specified just by that number alone, as well as time. Usually, time is used in seconds and it's specified by a number or its magnitude 5, 10, 20 seconds. That's all you need to completely explain these three. Three examples that I just showed here. Now, for vectors, on the other hand, so a vector by definition is a quantity that requires both magnitude and direction. So one similarity is the magnitude. Just as we've seen in the scalar, there is some number that represents a vector, but it also has direction. Like for example, we have a force. Somebody, let's just assume somebody is exerting a certain force along some object or whatever. Let's say it's 1 newtons. Now, this force has a magnitude. In this case, it's described by the amount of force. In this case, it's 1 newton. But it also has a direction. In this case, we could just, from a certain amount of angle with respect to x-axis, 30 degrees. So it has a direction as well. So that is the difference between a scalar and a vector. A scalar is just a a quantity that can be completely described just by its magnitude alone, like mass, kilograms, 5, 10, 15 kilograms, pounds, and such. A vector has both a magnitude and a direction. A vector has a certain, in this case, a force. It could be described by 10 newtons, 1,000 newtons, and so forth, but it also has a specific direction where that force is heading to. And so that's the main difference between a scalar and a vector. So when dealing with vectors, in this case multiple vectors, there is a certain way to add these vectors. The most practical application is dealing with a system with multiple forces acted upon, and so this is where we utilize vector addition. So let's look at two vectors here. So we have vector A pointed this way with some magnitude, vector B with another magnitude, and of course a different direction. Now, when you have, let's assume we have these two vectors acted on a certain object, whatever it may be. Now, what is the resultant force? Essentially, once you take account into these two vectors acting on this object, you could actually represent these two force vectors as just one. It'll be a combination of these two, and this is where we do vector addition. So, as I just stated previously, these two vectors can be combined such that we could simplify this system just by representing it with one force vector. In this case, let's call it R, which will be the resultant force. And so the resultant force is nothing more than the addition of A vector plus the addition of the B vector. Now, there are two different ways to solve for the resultant force. Here is the first way, which is known as the parallelogram law. So first, you connect both of these vectors at their tail. So the arrow is their heads and their tail is on the other end. You connect them both at their tail ends, and from here, at the one of the heads, let's say vector B head, we draw a line that's parallel to the A vector. So let's go ahead and draw a dotted line that's parallel. And we do the same for vector A. We're going to draw a line at its head parallel to vector B. So it's approximately here. Now at the point where these two lines intersect, this is where we draw our resultant force from the tail to the head. Let me redraw that real quick. So this vector from here to where the lines intersect, this would be our resultant vector, R here. Now, once you do that, all you need to do is use trig. There are two laws that you use. You use either the law of sines or the law of cosine. So let me go ahead and write this out. So just redrawing. So let's say we have this triangle here. Redrawing it up here, we renamed it to A, B, and C to generalize the formulas. For sine law, we have the side A divided by sine angle A is equal to B over sine B is equal to C over sine C. In this case, the lowercase letters represent the angles and the uppercase letters represents the sides. And the cosine law will be the C squared is equal to A squared plus B squared, take away 2AB, cosine the angle C. These are the two main laws you're going to be utilizing when using the parallelogram law for vector addition. And they are very useful, as well as it tends to be a shorter way to solve for these for the resultant force in certain instances. So let's go ahead and do an example utilizing the sine law and cosine law, as well as the parallelogram law for vector addition. So in this case, we have two force vectors, one 75 newtons and the other one 125 newtons, and we have the respective degrees with respect to the vertical axis as well as the angle with respect to the horizontal axis, in this case the x-axis. So we're supposed to find the resultant force and the direction. Again, we have two force vectors essentially, and they both can be represented to simplify this system as only one resultant force. Essentially, it'll have the same results if you have one resultant force as compared to these other forces. Um, just to reiterate, these two forces can be represented as one force only on the system, whatever it may be, some object, and that force is the resultant force in this case. So let's go ahead and redraw this, and let's utilize the parallelogram law. So both of these are already connected at their tail end. So let's start with the 75 Newton vector. In this case, we go to the head of this vector and we start to draw a line that's parallel to the other vector. So let's go ahead and draw a line as close as possible to parallel to that same vector. Now we do the same to this other vector. So now we go to this head and we draw a line that's parallel to the 75 Newton vector. So it's approximately here. And where these two intersect at this point, from the tail ends to that point, would be our resultant force, our R. So now that we have the triangles here, we could go ahead and use either the law of sine or the law of cosine to solve for the resultant force. So we know these two angles combined, we have the 20 degrees plus 35 is a total of 55 degrees. And essentially it's going to be the exact same angle here as well, 55 degrees. Now when it comes to one triangle, for one triangle, all three angles must equal to 180 degrees. Now you have two triangles, in other words, a square, they add up to 360 degrees. So we have 55, 55, that's 100, that's 110. That means this angle is 125 degrees, 125 degrees, as well as this one. It's the same. So now that we have this angle here, let me go ahead and just redraw this triangle. Instead of having both triangles, let me just draw one of. So redrawing this to have a little bit more clear picture here. So this vector will be our resultant force that we're looking for. And we have this angle 125 degrees. We do not know this one, we do not know this one, but we do have the magnitudes 125 newtons and this one's 75 newtons. So we do have one of the angles. So in this case, we could use the cosine law. Just keep in mind when it comes to the general formulas, we had it in terms of A, B, and C. in this case, we could just work our way to use the variables that we are using. So r squared is equal to 75 squared plus 125 squared plus 2 times 75, 120 times 125 times cosine 125 degrees. Actually, this should be a minus sign here. It should be minus 2 times 75 and so forth. So now just solving for r, we square root both sides to cancel out that square. And you just plug it into a calculator and this is your resultant force. So our resultant force is 178.9 newtons. Now for the direction with respect to the x-axis. Now this is where we could utilize the sine law. So remember, we have this resultant vector. We already have its 178 newtons, but we need to know its direction with respect to this x-axis here. So from here all the way to the resultant force, this is the angle that we're trying to solve for here. So one thing you'll notice is we have the resultant force and we have this angle. So be the 178.9 divided by sine 125. Let's go ahead and write that down. Now one thing to note is we already have this angle here, which is 55 degrees. It was originally given in the problem statement here. So all we need to solve is for this angle here. So we have 75 newtons, but we don't have this angle. So we have 75 divided by sine, let's call it, let's just call it b. So what is this sine b? So all you have to do is just algebra manipulations here, get sine to the other side, and then do the sine inverse. Let's go ahead and do that. So first you multiply sine b to both sides of the equation, and this is what you get. From here, you move the sine 125 over to this side, so you're multiplying both sides of the equation there. And then this is where you divide both sides of the equation with this one. So you're finally left with 75 times sine 125 divided by 178.9. And from here, our angle B is just essentially the sine inverse of whatever this is here. And finally, once you do the calculation, our angle is 20.08 degrees. But one thing to keep in mind, this is for our angle B, which was this one, angle B. But we were asked what is the angle with respect to the x-axis. So it's going to be this angle B plus 55 degrees. So at the end of the day, we have 20.08 plus 55. So our angle, let's just call it alpha, is equal to 75.08 degrees with respect to the x-axis. So let's go ahead and summarize this problem statement. So our original problem is we had two force vectors acting at this point. It could be, in reality, it could be on some object and such. And then we were asked to find the resultant force. So in other words, these two forces can be represented by just one force vector, which is the resultant force. In this case, we had two vectors. One was 75 newtons, the other one was 125. The resultant force was 178.9 newtons. But that's not only it. That was not the information needed. We also needed the angle with respect to the x-axis. In this case, from the horizontal x-axis, our angle was 75.08 degrees. So our resultant force is 178.9 newtons and about 75 degrees from the x-axis. So this finally is your answer to the problem statement. And this is essentially using the parallelogram law when it comes to force addition. Now there is another way to come up with the resultant force, which I'll be going over with in the next video.